In this project, our group strives to develop a firmer grasp on how we can utilize machine learning features, or as Spotify calls them, attributes, to determine the genre of a song.
Spotify's web API includes 13 attributes about each song. However, one detail that it lacks is song genre. In order to get a classification for song genre, we use Spotify's default curated playlist for a genre to classify instances. We took 7 playlists with different genres and gathered their respective JSON files for each playlist using Spotify's web API. We then converted the JSON files into a CSV file. The data we are training learners on has 13 attributes: danceability, energy, key, loudness, mode, speechiness, acousticness, instrumentalness, liveliness, valence, tempo, duration, and time signature. All attributes are continuous with the exception of mode and key, which are discrete. We leveraged these attributes to classify 7 distinct genres: EDM, hip-hop, classical, rock, pop, jazz, and country. We identified the genre based on which playlist the song was originally retrieved from.
We investigated song attribute distributions. We made histograms for each of the features and grouped the data by their genre. A quick overview of these histograms revealed some immediate results, showing that some attributes were homogeneous across genres, and no information could be gleaned differentiating the genres. An example of this is time signature. Almost every genre, except classical, had a 4-4 time signature, and it would be impossible to differentiate the other 6 genres from this data. However, some distributions were rather bimodal, and showed some promise for more complex classification functions. For example, for the energy attribute, classical music was skewed heavily to the low end, while rock skewed heavily to the high end. Ultimately, we used the histograms to determine what genres and attributes to investigate further. Next, we determined linear or logistic relationships across attributes or features. We made scatter plots comparing each feature with each other feature. We only compared features with continuous data points: danceability, energy, loudness, speechiness, acousticness, instrumentalness, liveliness, valence, and tempo. Possible positive correlations and linear fits between danceability and energy, danceability and loudness, danceability and valence, and energy and valence. Given that all these features describe songs that are high in positivity, rhythm, and upbeatness, it is not surprising that these relationships exist. Loudness and energy and loudness and acoustics follow logarithmic curves. We created a log model fit for these features in the notebook. Attributes, or features, that we did not find useful were time signature, duration, key, and mode.
Next, we wanted to experiment with a k-nearest neighbor learner to classify all 7 genres of music over a dataset. We trained and evaluated our scikit-knn learner using 10-fold cross-validation and took its mean accuracy. We yielded our best accuracy with a k equal to 3 and a feature set of danceability, energy, speechiness, and valence. Our accuracy is around 40%, but relative to a baseline classifier like 0R, which yields 12%, our accuracy is considerably higher. We had more success on more granular classification tests between 2 genres in our next experiments.
We attempt to train a model to classify if a given song is classical or rock. In another notebook, we do the same but with jazz and country songs. The 2 song attributes used to perform classical versus rock classification are danceability and energy. We use the gradient descent optimization algorithm to train a multi-layer perceptron cost function to classify these 2 genres. For the classical versus rock, of the 100 songs, we achieved perfect classification. For the jazz versus country, of the 153 songs, we achieved perfect classification.
We next wanted to experiment with unsupervised learning methods, specifically k-means clustering at the 2 and 3-dimensional levels. Using k-means clustering, we were able to construct 2 distinct clusters of classical and rock genre songs based on the features energy and danceability. By constructing a mesh grid and predicting each point within our grid using our learner, we can observe that there exists only one misclassification of a classical music song. The reason for this misclassification of this data point is the unusually high energy value of the point, forcing it to deviate away from its intended centroid. After this, we extended our experiment by adding acousticness as our third feature. From our 3D scatter plot, we could see a natural clustering of classical and rock songs along these dimensions. We're able to use k-means clustering to determine two distinct centroids, shown in green.
In conclusion, we weren't experienced with popular technologies and libraries to solve classification tasks, so this project gave us a good breadth of useful tools in the machine learning space. One important thing we learned was that it may be easier and more tractable to divide a generalized classification task into smaller, more granular binary or ternary classification tasks to achieve more accurate results. One challenge we faced was reducing the number of attributes. A solution we could implement in future work would be principal component analysis, where we would combine correlated attributes and reduce the dimensionality of our data. And the challenge that we mentioned earlier was that we had difficulty in classifying 7 different genres when there existed many correlated attributes and similar values over these attributes. Overall, we had a great time and we hope you enjoyed looking at our presentation. Thank you, and have a good break.